Okay, so we continue with the Deutsch Jozsa algorithm, which is simply the generalization of the Deutsch algorithm to arbitrary number of qubits. So first, for the uh, one interesting thing, so you have the 0 and you have a 1 and you have a C naught gate, and what really happens? So depending upon whether it's 0 or 1, this qubit, this bit gets flipped and you get a 0 over here. Now what happens when you have a superposition? Let's say you start with a 0. Uh, well, what you get over here is 0 0 plus 1 1 by root 2. That's the state you get. So the question you might ask is, can I write the state of the wire, any wire? This is, let's say, wire 1 of the circuit, this is wire 2. Can I write the state of the wire explicitly? Well, all I can say is that the joint state is and this state lies in the tensor product Hilbert space, or the vector space lies in the vector space. Uh, as you noticed, one cannot write the state of wire 1, for example, state of wire 1 as a vector in a two-dimensional Hilbert space in the usual sense. So, and this is a subtle message of entanglement, as we have already seen. So this is an entangled state, which means that a vector in 2D space describing the state of wire 1 is not possible. So you can say that is, in a way, a way to interpret entanglement physically. What it means, that a complete description is possible for the joint state as a vector in a tensor product vector space. So with that preliminary, we come back to the we come to the Deutsch algorithm again. So so as usual, you had the black box, and this was this guy, and you can start with the joint state. You can start with the state here. What you get out is x, y was giving you x, y plus fx over here. So as I said, we've already seen that, but it's still good to see that show u of f is unitary. Okay, and when x was this guy and let's say y was 0, we were evaluating so this is an example. We were sort of simultaneously evaluating the both values of the function on the single use of the circuit. And this is an example of what they call as quantum parallelism. Classically, to evaluate f0 and f1, one needs two circuits. But here, in some sense, there is an information about both the values on the single use of the circuit. And let's see, you have x over here. Now if it's fx is 1, then for example, let's say fx is 1, then y will flip. Remember, this is a binary addition. So uf is like a controlled flip operation. So for example of an implementation would be, let's say you have all these bits and this was your y and this could be your y plus fx. So this is a control knot, and in case all these x's are 1, 1, 1, 1, 1, I have 4 wires, y plus fx is going to be a controlled operation on all of them. If all of them are 1, then this knot gets activated and I implement this sort of a circuit. So in the circuit language, let's say if fx is a constant function, takes 0 to 0, 1 to 1, well then what will I have? I have, as a circuit diagram, a quantum circuit would be an identity operation, nothing happens, and I'll have y, I'll get an x, and I'll get a y plus fx. Since what happens? That's going to be the implementation of my u of f over here. Y plus fx is going to flip when fx is 1. So that's the idea. Here is my fx evaluation, because I have an x an identity operation evaluates f of x. Now the control depends upon the value of f of x. If f of x is 1, this guy is going to flip y. If f of x is 0, this passes through, and still I have y plus f of 0, which is nothing but y. So this is identity is in some sense the function evaluation, and the entire circuit is the evaluation of the u of f. Another example can be if f of x is this guy. It's a balanced function, but it just flips. How do I do it as a circuit? I have an x, I put a control NOT gate, now it is evaluating f of x. And I have a control NOT gate similarly, I have a y, this gives me y plus f of x, binary addition. And again I flip it x to recover x back. So this circuit again evaluates x, y going to x, y plus f of x, this circuit. So the bottom line is we can compute any function, any Boolean function, f of x, and then use it as a control flipped operation. Okay, so let's again revisit the circuit function evaluation in the Deutsch algorithm. I have my circuit. This guy. I have a Hadamard gate, and then finally I measure this qubit, and I have the H guy over here. And so what's really happening? I start with 0, 1, the state. Just give me a second. I'll get some water and be back. You think about the circuit. Yeah, so this was the state psi 1. State psi 2 is a Hadamard operation on both of them, so it's going to be this guy. Let me call this psi 0. This is psi1. Psi2, after my Deutsch circuit, as we saw, and one can check also, is going to be from the last class. This guy. So we can see the cases when f0 was f1 was 0, that's your case 1. Case 2 is when it's a balance function, f0 equals to 0, f1 was 1. Case 3 is when f0 was 1 and f1 is equals to 0. And case 4 is when f0 equals to f1 equals to 1. And that's going to give me a state this guy. This is going to give me a state evaluating this is going to give me a state -0 plus 1. And finally, this is going to give me a state so the bottom line is, in all these cases, what I get is, notice the relative sign of this: plus plus when the function was balanced, and minus minus when the function was constant, and minus when the function was balanced. So I can conveniently write this down as this guy. I'm going to ignore the global phase which is going to come, but that sort of is the idea. And in other words, I can also write this down as sum over x, where x is 0 or 1, minus 1 to the power of fx ket x 0 comma 0 minus 1. So here x is either 0 or 1, and it's just going to take the value. So that's a useful form. These two forms are sort of useful. We are going to use them to generalize what's going on. So that's the idea. Now look at it. So the bottom line is that all that boils down to the final state is, I'll include the global phase also. This was 0, 0 plus minus 1 to the power of f0 plus f1 ket 1, and then 0 minus 1. Okay, so with this insight that somehow the sum of these terms shows up as the thing that decides the relative sign between 0 and 1, that fact is going to be important for us. So you see, the information about the function shows up as a relative phase between this qubit. So that's how I'm able to extract information from the function, paste it onto the phase, and when I measure this qubit and some basis, that's going to determine what was the value of f0 plus f1, or whether the function was balanced, it was a constant function, so on and so forth. So that's the idea. If the function is balanced, then the phase would be minus. If the function is constant, then either this value is going to be 0 or 2, and then this relative phase is going to be plus. So generalizing this algorithm for n qubits is rather simple. I have a bunch of Hadamard gates. And finally, I have the 1 qubit and the Hadamard gate. Now I have my black box, again u of f, which is going to take my x, y to x, y plus fx. And then I have set of Hadamard gates again, and then I make measurements. Okay, so I can write down the state over here was nothing but sigma x, x tensored, 1 goes to 0 minus 1, so that remains same. And I'll have a 2 n by 2 over here. The state after applying the black box u of f is going to be the generalization of the other expression minus fx x 2 to the power of n by 2, 0 minus 1 by root 2. This guy. So one important thing to notice here is that, see what happens when I have a bunch of zeros, tensor product n, all this entire string, n, 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 and I'm applying a Hadamard gate to it. That's going to give me tensored into n, and in fact that's going to be, well, it's n root 2n to n to the power of 2 x, where x is all the bit strings 0 0 0 0 0 0 0 1 1 1 1 0 0, something like that. So this is called as the Welch Hadamard transformation, just a fancy name for something simple happening. Just want to label the page number. This is 4. This is 5, 6. Yeah. So for example, if I have 0, 0, and I add Hadamard transformation, that's going to give me 0 plus 1 tensored 2 by 2, and that's going to give me all the superpositions 0 0, just multiply it, 0 1 plus 1 0 plus 1 1. In other words, I get summation x, where x is all the strings, 1 over 2 to the power of n of 2 in general. And what happens when I apply a Hadamard transformation on one of these x's? Mind you, that's going to give me summation over z minus 1 to the power of x dot z summation over all possible cats over here. That's the idea. So, and some normalization over here. So, see, it's easy to see, for a single qubit, what does h0 give me? It gives me 0 plus 1 by root 2. h1 gives me 0 minus 1 by root 2. And if you plug this in, this is exactly the same form. H acting on 1, let's say x was 1, h acting on 1 gives me minus 1 x dot z. X dot z is going to give me 0 with a plus sign and minus with a 1 sign over here. So if I expand it, what I'm saying is the following. I have, let's say, a bit string x1, x2, xn. That's my bit string. It can be 0, 0, 0, 0, 0, 0, 1, 1, 1, anything, any x I put over here. That's going to give me a summation over z1, z2, zn. It's going to give me x1, z1 plus x2, z2, xn, zn, z1, z2, zn. Divided by this guy. Again, tensor n. So, in other words, this guy is a bitwise inner product of vector x and vector z. So, x dot z is exactly x1 z1 plus x2 z2 tick tick tick. This is the bitwise inner product of x and z. So now our message is clear. We have, I'll again let me see. Let me copy this circuit again. So what's going on? I had this guy over here. I had this state over here, and then I am applying the Welch-Hadamard transformation over here. So I am going to get a summation over z, this state, let me call it, so if this was psi 0, this was psi 1, this was psi 2, this is psi 3. So psi 3 is going to be summation over x, summation over z, this guy, 2 to the power of n, and the last qubit will be as it is, 0 minus 1 by root 2. So that's the idea. And now let's say z was all 0, 0, 0, 0, 0. In that case, the amplitude of all these bits being 0, 0, 0, 0, this guy is nothing but summation over x minus 1 to the power of fx 2 to the power of n. So if all bits you measure are 0, this was the amplitude of there. So if all bits so this gives you in fact the probability of measuring 0, 0, 0, 0, 0, and if it's a constant function, then that probability is 1, and that actually tells you about the function being a constant function. So the bottom line is, if all bits you measure are 0, this implies it's a constant function. This is precisely what we found out over here when we compactly wrote this example for a 2-qubit thing. Precisely over here. So after the Hadamard transformation, this is exactly what I'm going to get. And if all bits I measure are 0, then it's a constant function. Else, we conclude it's a balanced function. So, well, let's think about it. How is it, superior to a classical algorithm? Alice selects a number from 0 to 2 to the power of n minus 1, let's say some number over n, and sends over to Bob, who does a functional evaluation of f of x. And determines f of x. Now in general, Alice will have to send 2 to the power of n by 2 plus 1 numbers to Bob for Bob to conclude whether the function is a constant or it's a balanced function. So if Alice and Bob are allowed to use qubits, and Bob agrees to calculate f of x using u of x, then just one correspondence is sufficient. So in that way, how many times the Bob has to use the circuit. This provides an exponential speed up over the classical algorithm. So simply as a process, it was the implementation of this circuit, and then finding the probability all these bits come out to be 0, 0, 0, 0, 0, and that would be only true when the function was a constant function. Uh, so that was the idea of the uh, Deutsch algorithm, and I'll see you next time when we do something else. Thank you.